Hello everyone, my name is Muhammad Ali Jamshed, and today I will be introducing you to the basics of continuous time Fourier series uh, over CTFS, which is basically a fundamental of signal system, and this is the power of an ongoing course on signal and systems. So quickly about the content of the presentation. So I will start with some preliminaries, why we need Fourier series, what is CTFS, a quick mathematical analysis, key properties and insights, the practical applications, quick summary, providing you with the key take-home messages, and in the end, we will do a quick task and a brainstorming session. So this is some of the resources. I hope the students should have a basic understanding of what Fourier series is. And then if they want to learn more about the Fourier series, they can use this book, these two books, these two resources, which I have also used to prepare this lecture. So a quick motivation. So when we talk about the real world signals like AC power audio signals, heartbeat signals, they are represented in the time domain. So and they are very complex. So in order to understand or to find the hidden pattern behind those signals, Fourier series provide us an opportunity to convert that time domain signal into frequency domain signals to get to know about the hidden pattern and to enable efficient processing. So when we talk about the what CTFS does, it decomposes a periodic time domain signal, say x of t, with p of t into sum of sinusoidal blocks like sine and cosine. So why we need to break down that signal? Because again, like the complex signals in real life, like heartbeats, square waves, they are really hard to understand to do a time domain analysis. So what Fourier series or Fourier CTFS does is to provide a frequency domain version of that signal, which can help us to analyze the signals more effectively. So a quick mathematical representation. So a CTFS signal is represented here as x of t, which again, a signal has two components, two main components, that amplitude and phase. So A naught is basically representing amplitude, and this is basically defining the sine and cosine function of the signals. So where omega is the frequency component, which is the lowest frequency component, where n omega naught is the high frequency component that increases with that are the integer multiples. So in order to calculate the Fourier coefficients like a naught, a and bn, we use simple integration. And one thing that we need to keep in mind that these all integrations are performed over one complete period of the signal. So if you look at the representation, these signals are a bit more complex, and it's a very a big equation. So in order to present or to convert that signal into more compact form, we use this complex exponential notation like here. So what it does, it helps to make mathematical notation more compact, combines amplitude and phase information into single coefficient, simplifies the linear analysis, provide direct link to frequency domain concepts. So the few key insights that we need to remember. What are the key properties? Basically, one key property that we need to remember is dielectric condition, that the signals need to be periodic in order to CTFS for exist, and the signals are orthogonal, they are independent, and they only frequency that are integer multiple frequency, fundamental frequency omega naught appear in the series. So practical applications, it is used in signal filtering, modulation, demodulation, in audio image compression and circuit design. So a quick summary. So basically, CTFS represents the periodic signal as a sum of complex exponential. It helps to analyze the complex signals in a frequency domain to understand the hidden pattern and provide us an opportunity for efficient processing. Its application spans on communication, control system, and digital signal processing. So a quick brainstorming task, like in order for students to understand in more depth about CTFS, I would request students to do a task. The task is basically about using the CTFS to reverse engineer a square wave. The key question that needs to keep in mind and that needs to be addressed, it's number one, what do you notice about the signal as you add more harmonics, more frequency harmonics? What do you think higher harmonics are needed for sharp edges? How might this relate to real world system like audio digital signals? So here I would like to thank you. And if you have any questions, please feel free to ask. And if you have any further questions, please feel free to send me an email. Thank you for listening.